Hi everyone, I'm John Mo from the Department of Civil Engineering and Engineering Mechanics of Queensland University. Today, I'd like to introduce my work of physics-informed deep learning paradigm for car falling models. Car falling modeling is important. For example, in the safe driving algorithm, it's very important to learn how humans drive, how humans react to their leaders. In the simulation platform, it's also important because the car falling models are usually built in to simulate the environment cars. So in the problem of the car falling models, there are very important questions. How can we predict the accelerations based on the current states? So there are basically three main types of models. The first one is the physics-based models. So which use some prior knowledge, just like some physics information, like the ordinary differential equation, ODE. So the physics information can be also some constraints, like monotonic constraint. It can also be some like kinematic equations. The second type of model is the data-driven models. So instead of make any prior knowledge or prior assumptions, it uses deep learning methods like the neural network to learn directly from data. So that's why it's used. It requires the amount of data. So in a third type, we propose the physics-informed deep learning, the PIDL. So which is essentially a combination of these two models. So we want to use the physics-based model to regularize the training of the data-driven models. So our ultimate goal is like, if you use the physics information, you can use less data to achieve the similar or even better performance compared to the data-driven model. And in this table, we summarize the similarities and the difference between the physics-based model and the data-driven models. So their input and output are the same because they are trying to serve the same car falling problems. So the inputs here include the headways, which is the distance between the leader and the host of vehicle, the velocity of the host of vehicles, and the velocity difference. So which is the velocity difference between the leader and the host of vehicle. With the inputs, our output is the accelerations of the host vehicle in the next time step, which is the target acceleration that this vehicle wants to achieve. So there are huge differences in the parameters for these two models. For the physics-based models, the number of parameters is usually less than 10. However, for the data-driven model, the number of parameters can easily goes up to like 1,000 or 1 million. So for example, there is a very simple neural network, a two-layer network. It has two hidden layers, and in each hidden layer, there are like 30 nodes. So the number of parameters, just in these hidden layers, the number of parameters is like 30 times 30, the weight, which is 900. So it's around 1,000. So it's only a very simple neural network. Okay, with the notation here, we are ready to introduce our proposed physics-informed deep learning structures. So in this structure, we can see there are two parts. The upper parts, we use there are two components, the physics component and the data-driven component. In the upper part, we use, in this example, we use the intelligent driving model as a physics component. So in this model, we have 5 physics parameters. Those parameters all have the physics meanings. For example, the Amax is a maximum acceleration that a vehicle can achieve. From these physical equations, we can construct a physics-based computational graph. In this graph, each node represents either inputs and outputs or some intermediate value. And each edge so each square represents the previously mentioned fixed parameters. And in each edge, there are just some simple operations like the addition, subtraction, multiplication, and division, or even the square root. And in the lower part, we just use a neural network as the data-driven component. So it was mentioned that we use the neural network because it's the most representative model, the data-driven model. We can also use other framework or other model like the LSTM or the recurrent neural network. So there are two types of data used here. The first one is observed one, the observer states or the label states. So it's labeled because we have the corresponding observed accelerations. So it's just a state acceleration pair. So another type of data is the collocation states. So it's unlabeled, which means we don't have a corresponding ground truth. So and instead we use the fixed-based complexity graph to make prediction. The whole training logic is like we use observation data, observed data to be fed into the neural network to get a prediction. And we compare this prediction to the ground truth value to construct a mean square error for the observation data here. On the other hand, we input the collocation states to both the physics model and our neural network model. And their outputs are compared to each other to construct another mean square error. So this error is the physics loss function or the fixed mean square error. And this mean square error is so-called the data mean square error because it's learned directly from data. And this one learns from the physics. So our final loss function is constructed by a weighted sum of these two mean square error. So here the alpha is hyperparameters, which control the ratio of these two parts. So we can call the 1 minus alpha as the ratio of for the physics, and the alpha is the ratio for the data. For example, when the ratio with the 1 minus alpha equals to 0, which means we only relies on the data part. And when the 1 minus alpha equals to 1, which means we only use the physics model or physics information. By minimizing the loss function, we can update both the theta, which is the parameter for the neural network. We can also update the lambda, which is the parameters for the physics information, physics model. Okay, with the PIDL structure, the physics informative learning, we apply this structure to a real-world data set, which is the next generation simulation data set, the AGSIM. It contains vehicle GPS trajectories collected by bird view cameras for every 0.1 seconds. The result is shown here. So we compare our PIDL structure to the baselines, which includes a pure physics model and a pure neural network model. The physics model here is just the IDM model, intelligent driving model we mentioned before. From this figure, we can see that our proposed model outperforms the baselines. So especially when the number of trained data is sparse. So for each number of trained data, we also record the optimal ratio of physics, which is the 1 minus alpha here. For example, when the number of trained data equals to 1, we try different values of 1 minus alpha from 0.1 to 0.9. Then we find that when 1 minus alpha equals to 0.9, it can achieve its minimum error. So that's why we record the 0.9 here. So similarly, you can record the other points for this curve at different number of trained data. From this curve, we can see that the optimal ratio of fix just decreases when the training size increases. So the reason is like when the number of trained data is poor, when the data is sparse, we cannot get enough information from the data because we don't have too much data. So we have to rely on the physics to get some information. So that's why the ratio is large, because we can rely on the physics to train the model. On the other hand, when the number of data is big, when the data is enough, the data itself can provide enough information. So we don't have to wait too much on the physics. So that's why the ratio here is just like 0.9, which means 90% of the loss function come from the physics. And here, here is a 30% of the loss function come about from the physics. And here, when the data is sparse, like the 90% of the mean square error come from the physics. So there are two conclusions in this work. First is like our PIDR model contains two parts, a data-driven one and a fixed components. And our experiment shows that our model have the advantages in both the accuracy and the data efficiency over the baselines. That's all for today, and your question is welcome. Thank you.